Welcome back, students. Let's go over to some more examples. Well, let's go back to this example. A certain college selected a random sample of 100 commuting students and obtained the students' one-way commuting distance. The resulting sample mean was that, so that is the center. This is the center of the normal picture. And then sigma was given, so we have to calculate SC, standard error, sigma over square root of n. And this time, let's look for, well, 98% confidence interval. Okay, let's go ahead and do that. Here is the visualization and some computation too. We have this normal picture around 10.22. And the middle area is 98%, 0.98. So left hand side we have 1%, right hand side we have 1%. And which is easier to deal with? The left hand side. So let's look up z-score associated to 1% from the z-table. Let's see, here's a z-table, and we need this blue area to be 1%. So where is it? I think we have it here. Oh, okay, around here. Negative 2.32, we get 0.0102. Negative 2.33, we get 0.0099. And let's see which is closer. Looks like this is closer, so you can use this. Negative 2.33. In short, the z-score for this case, z-score, which is end minus center over SE, has to be, approximately speaking, negative 2.33. But then again, by symmetry, we have negative 2.33 here. This one will be positive 2.33 by symmetry. So as usual, this will be equal to plus or minus of that, and we end up with this kind of equation. End will be, well, mu. Where's mu? Okay. Mu minus 10.22 over standard error we calculated before, 6.0, is approximately negative 2.33. And then if this is positive 2.33 and flip the denominator to the other side, in the end you'll be able to find this mu equals to something. Equals to, well, something. Mu equals to, well, something. Finishing this computation, you're gonna get the solutions. Can you do it on your own? Pause this video and try to do it. Well, okay, let's open up the solution, and here we go. And it's 100, so standard error is 6.0 over square root of 100, so it's 0.6. And then n minus center over standard error is plus or minus 2.33. So from this equation, flip denominator over to the other side, we get about 8.822. From this equation, flip the denominator over to the other side, you get 11.62. As a matter of fact, this should have been mu2. Consequently, we get this confidence interval, which is actually a 98% confidence interval. 8.82 to 11.62 approximately speaking. Here in this program, I use Mathematicus computations. So instead of 2.33, I get a little bit more accurate figure here, 2.32635. Consequently, we get a little bit more accurate figure here and there as well. But the normal table will do in our level. Now, what if we have just one-sided interval and looking for confidence bound, upper confidence bound or lower confidence bound? In any case, it's going to be a good idea to draw the picture. This kind of thing is about upper confidence bound. We have 95% here in the blue range, and then red part is 5%, centered around 10.22. So how do you find out this end value? Well, you have to use the z-score associated to this entire blue part of 95%. In short, this is what you have to do. Z-score is end minus center over standard error, and then that's approximately, in this case, end minus 10.22 over 6.0. No, excuse me, 0.6 is the standard error. And that has to be the z-score associated to 95%, because this blue area over here where I'm moving my mouse around is 95%. So look up 95% from this z table. Let's go down here, 95%, 0.95. Well, I have it around here, 1.64 or 1.65. So let me estimate it as 1.645, 1.645. Okay, let's go ahead and do that. Then this will be 1.645. This time no plus or minus, because this is not symmetric. I don't see anything the other side, so just positive 1.645. And well, from this, setting this one, from this equation you can find out the end. Can you do it? Well, here it is. This one is that, and from that we get 11.207. And what if you use negative? Well, this doesn't contribute because we want upper confidence bound. Only this one, the second line, gives you the valid number, upper confidence bound. You can do the same thing to find out the lower confidence bound as well. Let's see, do we have enough time for another? Yeah, let's go over to 1.5, determining the sample size. Suppose that the weight of boys in a certain school district is normally distributed with a standard deviation of about 3 pounds. Determine the sample size in order to estimate the mean weight within 1 pound with 95% of confidence. This time we don't know the standard error. Sigma is 3.0, but standard error is, you see, sigma over square root of n, and that's going to be approximately equal to 3.0 over square root of n, and that's it. Because we do not know the sample size n, we cannot go any further about the standard error. But is that enough to determine the setting? Well, it turns out it is okay, as a matter of fact. Let's begin with a visualization. And here we go. We want 95% confidence, so 95% here, 2.5% there, left-hand side, 2.5% there, the right-hand side. Here we have 95%. And we want to estimate within 1 pound, which means the estimate, the point estimate, and the end, the distance from the center of this interval toward the end of this interval should be 1 pound. Should be 1. Distance x bar to mu2 will be 1. Or if you want to do it the other way, that's fine too. X bar to mu1 will be 1. How do you go further than that? Well, here we go. Mu2 minus x bar has to be 1, alright. And actually, to be really precise, I use absolute value figures, but everything is positive if you do mu2 minus x bar, so you don't have to worry about absolute value. I use absolute value signs because I'm a teacher. So okay, 1.0 is equal to mu2 minus x bar. Okay, alright. And what is mu2? X bar plus z times the standard error. And z is the z-score associated to 95%, 1.96. So this whole thing is 1.96 times 3.0 over square root of n, see, as you have calculated on the right hand side. This x bar and that x bar cancel each other out. So what do we have? We have this equation here. 1.0 is equal to, approximately equal to 1.96 times 3.0 over square root of n. Solving this equation, you're gonna get square root of n is about 5.88. Taking the square, we get n is approximately 34.57 something. But you cannot select decimal number of people. So in order to satisfy this, you have to round up. Even if you have 34.10 something, you have to round it up because you need at least, this interval must be no greater than 1 pound. 1 pound is the limit. You have to do it more accurately. In order to do this sampling more accurately, you need bigger sample size. So always you round up. You need at least 35 randomly selected boys here. Let's go back here. The distance from the center to the end is z times se, because this is x bar plus z times se. This is x bar minus z times se. The distance is z times se, so z times se equal to 1.0. That's how the equation is forming, and that's how you can determine square root of n. This was one of those high-end problem because it was backward problem, but still, this is one of those problems that was covered in the textbook and also tested in WebAssign multiple times. So you gotta know these kind of things.